In this video, we will learn how to use the Fluent software, and we will do a small simulation of a very simple case with a liquid transporting with the internal flow of a confined with a solid surface, and it will be quite simple to understand the Fluent on the very basic step. So I will give you information related to the interface first. But do remember that as I had told you in the previous video that CFD composed of the steps like pre-processing and processing and then post-processing and then modeling. So in this video, the initial stage is already be completed. Like we have developed the geometry and we have defined the meshing. Although we will check out the meshing quality as well, but the initial part uh, has been done. So we will move forward, solve the case, and then we will try to uh, do some post-processing activities. Okay. So let's suppose, first of all, I would like to give you information about if the software is installed in your system. So you just need to turn it on here with the option coming up here in the window with the name of Learn. 16.2 is the model which we are using right now today. So our case is 3D, and we want to solve a 3D model. Okay, you can solve it a 2D model as well, but right now we are interested in developing the results or solving the solution, which is 3D. Then we have two options related to the double precision and mashing mode. So right now we are selecting the double precision option. Then there are other options available related to the display wise. So we are selecting both these option as we know that the mashing is already be maintained. Okay. Then at the last we have processing option in which we have serial and parallel. So we can utilize it, but in my system we have only selecting as per the configuration of the PC. I'm selecting a serial processing option. Okay, so just click on OK so that our software will, once its opening window is appearing, it might take a bit longer, so you should wait it and do not do command in between of that. Okay, so first of all, there are certain compartments or portions of the software. At the top or bar portion, we can see there are different icons available here, and those icons can be also be maintained in different portion of the bottom windows. So this first window, which is available in this portion of your software window, is come in the category of project model tree. So whatever you will start, you will define, everything will come in this portion of the window. Like we will initiate our process, initiate our simulation. We will develop some setup, and then we will define the general uh, uh, things, and then we will select the materials. Okay, and then we will move towards the solution, or you can say the processing part of the our simulation part. Okay, so everything will appear as a tree in this portion of the window, which is classified as project model tree. Then we have the second option or second portion of the window, which further elaborate the options which is mapped with the project model tree. And this portion uh, is named as sidebar window. Okay, and then we have this light blue to blue uh, window, in which we have XYZ uh, uh, access also available. So this window is simply categorized as the graphical view window. Okay, and at the bottom of the graphical view we can see there is a console, and this is a text console in fact, and it give us the information about the right now whatever the software running, processing, solving, or maybe we evaluate it in order to like if we want to rectify the quality of the mesh. So all the results will be appearing on this bottom part of the window, and that's simply known as with the name text console. So as I had told you before that uh, our geometry is maintained and we need to import it right now in this system. So we will go to the file, and then we will go to the read option, and then we will go to the mesh option. So we will go to the read, then select the mesh file, and our mesh file is located mm, in the downloads. Okay, so it's appearing with the name of MSH. So we will just import it into the software. So here again, the text console providing us the detail about the main working of the software, and it's representing that some geometry has been uploaded and the work is done. So first of all, we will have the geometry successfully available in this screen. So we will wanna move on to this window and select the display option, and we want to display our geometry. So it's now available. Okay, and we can see it with its defined different components. So one by one, if we uh, just select that inlet, inflow 1 is here, and then we have inflow 2, which will be available in this portion. Okay, and then we have outflow. So the outflow will be this, and accordingly we will define the process conditions and limitize our process. And then we have pipe 1, which is defined with this geometry, and then we have the final pipe 2, and this is representing the whole geometry of our case. Okay, so we just select the display option so far. Now we will move towards our second option, which is available in this portion of the window, and it's we want to check the quality of the meshing we have maintained in our defined geometry to solve our case. So let's see. uh, Now here there are certain uh, factors which is defined by the software in console, and the volume along the x-axis, y-axis, and z-axis are available now, and volume statistics in its magnitude in cubic meters are available, and ultimately the minimum uh, face area and the maximum face areas are also available with checking match. Okay, and that again representing that the that task has been done by the software. Now we'll move towards the report quality or the mesh quality to evaluate it, and we can see that our orthogonal quality is coming in the range of 0.40, and the range is also available at the bottom portion of the result. Okay, so our range is lying in between of 0 to 1, which is a comparatively good uh, reflecting the quality. Like if it's going closer to the 0, that will reflect our low quality meshing. Okay, then we have maximum ortho skewness, so which is again around zero point 0.5, and its low quality values are near to the 1, and we can see clearly that our value is very far away from the low quality mesh. So it is considered to be a medium quality uh, meshing work. And then we have an aspect ratio as well, which also representing the quality of the mesh. Now all is done. Now we will move towards the solution or solver specification. First of all, we need to identify that our system is a pressure based or density based. So our system is a pressure based because it does not contain a very high velocity or high Mach number in our system. So we will select the pressure based solution characteristic for the solver. And if our Mach number is coming in the category of supersonic, so on those cases we are supposed to select the density based solution, and that ultimately affect uh, the density of the fluid because of the high shock rate. Then there are other options like velocity formulation. So we will select the absolute velocity formulation option because there is no relative velocity of the solid surface, or there is no solid surface moving around with respect to the axis. So our system is we will consider all the solid wall surfaces at a stationary level, and on the basis of that we are going to select the absolute velocity formulation. The third option is steady or transient. So for that, obviously we are at the beginning part of the CFD understanding. For that, we are first of all want to understand or the solution based on a steady state. Okay, now this portion is completed. Now we will move towards our second option of the main uh, tree, solution tree, and we will go below then the general option, which is general. Now in general, we have further options like it's not a multi-phase system. So again, we confine it as off, and then we have energy equation. So what we are supposed to solve in this solution is there is a one type of fluid with a particular temperature will enter to from this cross-sectional area. Let's say this is the A1 area, and then we have another inlet area for another type of the fluid which possesses different temperature as compared to what entering at the first portion. So again, both will mix up here, and there certainly the temperature changes occur, and on the basis of that, there is certain energy transformation took place within our process. So on considering the scenario, we are going to turn on this energy equation, okay, and by double clicking you can select it, and you need to just check it, uh, the option to turn it on, okay. Now, our system is, let's suppose, in the turbulent region, and how you will optimize or rectify that whether the system is laminar or turbulent or in critical region. So simply you need to calculate the Reynolds number and just classify it whether the Reynolds number is coming in the limit of laminar region or turbulent region, or maybe in the critical Reynolds number region. So we are considering our system as the turbulent region, and the flow characteristic as turbulent. And for solving our case, right now we are selecting the model as the standard K epsilon equation. And for that, we are selecting the wall standard wall function as well, which is available here. Okay, so we will make sure that it is properly checked. So just click the OK. Now there is no radiation in our model. Heat transfer does not heat. There is no heat exchanger in our system. So all these further options will remain turned off, and we will not modify it. One more thing you can I want to add it that if we are selecting the k epsilon model, so we can also modify its model constants as well, if we want to validate our results and they are not matching with our exact results. So CFD is not all about to simulate the case. It's all about that you need to understand that how smartly you can get the realistic data from the simulation. Again, it's very critical, and for that things you need to modify certain model constants as well, or sometimes you need to optimize the selection model of you're supposed to select for your case based on your scenario from all these lists, which is available for the turbulent region. Okay, so now all is done from the model because we have select two fundamental equations. The energy one, we turn it on, and the second one is the viscous flow, for modeling the viscous flow or turbulent flow. For that we have selected the standard K epsilon standard wall with a standard wall function. So the next part is the materials, and in materials we gonna select the air, okay, and we will go to this option, create and edit, okay. A comprehensive data is available in ANSYS, okay, which is available here. If you want to select any other type of uh, compound, or you know the chemical formula of the substance, so you can extract out its property for a particular case. But right now we are going to select the air, okay, so we will not select anything from the Fluent database. Apart from that, there is an option of user-defined database, and for that, you are supposed to define a substance. Like if you want to simulate a process which contains milk, obviously the milk is not available in the Fluent database, so you need to define it by providing essential properties related to the milk. Okay, so right now our system is quite simple, and we are selecting the air and its density, and we're considering it as a region where the air behavior is ideal. Okay, so after selection, we wanna select the option of change and create, and then we will close it. Okay. Further, there is no solid and other things, so we just leave it remain as what as it is. Then the next option is about cell zone condition. Okay, and we have uh, fluid one here option, and the type of the fluid is also available. So there are two options here, the solid and the fluid. And as we know that our system is comprises of the fluid, which transport from two inlet with different temperatures, and the exit temperature will be at the downstream after mixing it will be again different than the each inlet uh, temperature. So we will remain it as fluid, okay, and we will not gonna change anything here. Fluid one, okay, all these value will remain same. Now, if our system is something like it's running in 2 bar or 3 bar or 4 bar condition, so we have to notify it here. But right now we are considering that our system is running at atmospheric condition, and the pressure of the operating pressure of our system is 101,325 Pascal, so it will remain as it is. So we all done here. Now we will move towards our another primary tree, which is the boundary conditions. Now we need to define the boundary condition identically for each portion of our geometry or as per the scenario. So first of all, the inflow one. So first of all, we have numerous options available here. Type, and we can select a lot of types, but here we are selecting the velocity inlet type, and then further in this option we have numerous like momentum and thermal. Apart from that, we have remains closed the radiation species, multi-phase component. So we need to define only two of these factors or these values available in this option. So first of all, we have velocity magnitude method, and it should be magnitude normal to boundary, and there are other options as well, but as per our scenario we are selecting this option. Then as discussed before, that our system is absolute, there is no such relative velocity available in our system, and all the solid surface we are considering as stationary. Now we are considering the magnitude of the velocity at uh, inlet 1 as 1.5 meter per second. Okay, and then the we also considering the gauge initial gauge pressure as 0, because the operating pressure which already we have defined as an atmospheric condition. Then there are other two options like turbulent intensity, so we are allowing here 5%, and turbulent viscosity ratio, which we have to change because we want to solve our system with um, in intensity and hydraulic diameter option. Okay, so and here we will define the hydraulic diameter value as 0.05. It's done from here, momentum option. Now we will move towards the thermal option, and in thermal we are selecting the 300 Kelvin and make it okay. So inflow one is properly defined. Now in the same way we are going to define the inflow two, and with the same way we will select the velocity inlet. Okay, and we need to edit it. We will define the momentum. This option will remain same. The absolute reference frame is again remain same. The velocity here we are defining as 1 meter per second, and again the operating condition, as we know that it's 101,325 Pascal, so in gauges it will be 0. And the specification method, Previously we had select intensity and hydraulic diameter, so we will select here in the very same way. The turbulence intensity percentage is 5%, and hydraulic diameter here we are defining as 0.04. And in thermal, we are defining the temperature as 400, which is different than what we have placed uh, in flow 1, or the inlet characteristic of the flow of air at inlet 1. And we will press OK. Now, the third option is outflow. And again, we need to select the type, and here there are numerous options available, but as per our process, we are selecting the pressure outlet, and but we need to further define our uh, values for momentum and the thermal taps. Okay, so again, the gauge pressure is 0. There is no radial equilibrium, average pressure specification, target mass flow rate. So we are not going to check any one of these, but we need to define the specification method on a very same way, which was intensity and hydraulic diameter. With the same way, we are notifying the turbulence intensity 5% and the hydraulic diameter as 0.05. Okay, and in thermal, we don't know the temperature, so we will not gonna touch or modify its value. Software need to simulate it and predict the final value of the temperature. Okay, so now it's done. Now we will move towards the 5.1 geometry. We will define it. So we can see here the software autonomously select the wall. Okay, um, and then we have other options. We will go for edit, and as I had told you, there is no we are considering all the solid surface as a stationary surface, so it will remain stationary. And obviously when the surface is stationary, there should be some no slip conditions also available within the geometry. uh, the reference height will remain 0, and the reference constant will remain 0.5. Okay, now we will move towards its these properties depend upon the material of your system. Okay, here if we are considering the system as there is no heat is dissipating, and so for that we will make sure that the heat flux is 0, and now we are on the same way. We'll press OK. Then we have 5.2. It's again automatically the software selected as a wall, because all these things already been defined in while developing the geometry. Okay, but we need to further define the further values, like it is stationary, and it is a stationary. There will be no slip condition, and on the very same way we have uh, these constant values depending on the material which we have selected for the solid surface. Okay. Similarly, we will make sure that the heat flux value should be 0 here, and the material is same. Okay. So we'll do this press it okay, and all is properly defined in this section. Now we will move towards there is no dynamic mesh available reference values requirement. So we will directly move towards the solution. First option, which is solution method. So first of all, we are going to solve it with a very simple uh, method. So the software is asking us about pressure volume coupling scheme, and we will notify it as simple, although we have other option as well. Then we have gradient, so it will remain least square cell based. Okay, and then we have pressure. So although here it is selected at second order, you can solve it with the second order, and second order will provide you a very accurate result as compared to this first order upwind method. So in pressure, we will select the standard, And for density, we will select the first order upwind. And for momentum, again, we will select first order upwind. Then we have turbulent kinetic energy, first order upwind. Momentum equation as first order upwind, turbulent. Every option is selected as first order upwind, including energy. Okay, you can solve it with the second order upwind as well, but as covered in the theoretical class, that uh, first order upwind provide you the result, but second order upwind is more accurate and provide you a more accurate result. So now we have defined all the solution methods. Now we will select the solution controls. Okay, for solution controls, we have the value for pressure, density, body phases, okay, momentum, and turbulent kinetic energy. So we are not going to change it, and it's all uh, correct. Now we will move towards our monitor options, and in monitors we will select the residual part, okay, and we will select the edit option, and in edit we will make sure that print to console and plot are properly checked, okay, and the window is 1, the iteration is 1000, store to 1000, okay, and then we have residuals about the different equations that up to how much accuracy it needs to work on. So all we are moving, try to solve it up to 10 to the power minus 5, okay, so we will make it on a very same way. It is 10 to the power minus 6, it's more better, so you're not gonna disturb it. And the same way all the options are selected as 10 to the power minus 5. Now we have normalize option, iteration 5, which we cannot change, absolute, our system is absolute, okay, scale, and computer local scale, so we are selecting the scale only, and just pressing OK here. Then we have other options like surface monitor, so we are going to create it, okay, and in surface monitor we are selecting the ASD maximum, and we will make sure that both these should be checked, and we need to find um, the flow out outflow characteristic, and we should select the temperature. Temperature should be static here. X-axis is iteration, get data every one iteration. um, so we don't need to check it, all is defined now, and now we're gonna press the option OK. After that we will going to further the main tree, which is here, and we will press solution initialization. In solution initialization we have two options, hybrid initialization or standard initialization, in which we are selecting the hybrid initialization, and we will press the initialization, so our software has initialized it, okay, and mm, further we don't need to utilize more options, and now we will go to our calculation activities, and autosave every iteration. So we are selecting 30 here, Okay, and after selecting it, now we will move towards the running calculation. And first of all, we are going to define the number of iteration which we randomly place the value. Approximately means like so that the software can solve it up to because it's not a very complex solution. Otherwise, sometimes we need to give the value of 1000 or 1500 on the basis that the solution cannot be converged, and these are a small uh, quantity of the iteration. And report interval is 1, profile update interval is again 1, and now we will press the button uh, calculate. Now it's solving our system, and let's say all the equations residual are available here. Okay, it should be moving towards the reducing trend. Okay, and we can clearly see that 10 s to power minus 2 to it is moving towards 10 s to power minus 5, which we had defined in our setup. Okay, so right now our calculations are complete, and we can clearly see here in our uh, text console that the solution is converged to the defined value over which we want to get our answer. So we will select OK, and we can see the geometry of our solution. Okay, and now we will move towards our results. Okay, and in results we can go to the option report, and there we can select the fluxes option. Okay, and we need to press the setup button. Then we have a mass flow rate option, and we are selecting all these options where the flow rate is developed. And then we press the button compute. So ultimately it will solve our solution with this. Now close it, and now we are moving towards the graph. Okay, in the graph we will select the contours, and in contours we have to set them up. Okay, so here are different options up to which you can develop a wide range of results. So here I'm temporarily selecting some of the variables, like we are supposed to calculate the final temperature, and so it's better to select temperature contour. If we select the pressure contour, we know that our system is running at atmospheric conditions. Okay, and it should be static. Then we have minimum value and maximum. The software will automatically select it. Okay, level 20 to 1. Okay, and we need to select two portions, and with that we need to press the button display. So now we can see our geometry with the defined gradient of the temperatures. Okay, these are the different values of the temperature from, you can see, 300 to 400, and in Kelvin. Just press close. So this is all about the very simple method through which you can simulate any case. Right now, even we don't have developed the post solution activities or modeling activities. It will just give you a comprehensive information or essential information about the software interface and the options you can opt while solving any simulation. So for today, it's enough. In the next video, we will discuss the post-processing activity, or the post-processing results that we can generate with the help of uh, answers, or even how can we develop a model or correlation with the help of different variables in order to investigate that how our process depends on various variables. Okay, so that's all for today. Thank you very much.